Hello YouTube friends, in this video I'm going to be proving to you geometrically, visually and algebraically that when you get the cubes of natural numbers up to the term n, you end up with n squared over 4 multiplied by n plus 1 squared. Now, to get the same proof as me, there will be 3 things that you need to know. Number 1. When you sum up all the natural numbers up to the term n, you end up with n over 2 multiplied by n plus 1. Number 2. The area of a square is its length, multiplied by its height. Number 3, and this is absolutely crucial, n over 2 multiplied by n plus 1 squared minus n minus 1 over 2 multiplied by n minus 1 plus 1 squared, is equal to n3, or n to the power of 3, and n is equal to the amount of terms which exist. Now, don't worry too much if you don't understand why you need to know these 3 things. I'm going to be explaining absolutely everything to you in detail in this video. Okay, I'm going to get started with showing you how to come up with this proof. The first thing I want you to do is turn your attention to the diagram to the left, and what you will notice is that the length of this square, the large square, is equal to number 1 over here, this formula over here. Now, the same can be said about the square's height. It is also equal to 1 plus 2 plus 3 plus 4, etc., etc. If you look at the diagram carefully, you'll notice this. So, the length and height of the big square is equal to this formula over here, and that is the same as n over 2 multiplied by n plus 1. Now, if the length and height of this big square is n over 2 multiplied by n plus 1, what do you think the area of the square, the massive square, is going to be equal to? Let's see. So, the area is length times height, and we know that this is going to be equal to n over 2 multiplied by n plus 1 multiplied by n over 2 multiplied by n plus 1. And this is in fact equal to n squared over 4 multiplied by n plus 1 squared. So this is the area of the big square, and it's actually related to what I'm trying to prove to you over here, that when you get the cubes of the natural numbers up to the term n, you get n squared over 4 multiplied by n plus 1 squared. Now, you've looked at this diagram carefully, you've paused the video, you've listened to what I've said, you've done everything you had to do to understand why the area of this big square is n squared over 4 multiplied by n plus 1 squared. The next thing you will have to understand now is what each part of this big square is individually, because we are going to need that to get our proof. So we need to know what this part in orange is, what this part in brown is, what this part in purple is, what this part in grey is, in blue, in red, in green, and in yellow. These areas make up the entire area of the big square. And by knowing them individually, we can get our proof. Alright, you may be thinking that getting the value of each of these areas individually is going to be very, very tedious. But that is not the case. If we come up with one general rule, okay, like this rule, which is number 3 over here, it becomes very, very easy and simple to get all of these areas individually. Okay, we only need one basic and simple rule, and that is this rule number 3 over here. Now, if you understand this over here, I guarantee you that you will understand this proof in its entirety. And guess what? I'm going to explain to you exactly and in detail what it means. Now, to understand this over here, let's turn our attention to the diagram once again, okay? And let's find this area in orange, okay? How are we going to go about doing this? Well, the secret is getting the area of the entire square, okay, and then subtracting the brown square from it, okay? So let me explain this more clearly. We get this entire square, okay, I know this isn't very straight here, these lines, but we get this entire square over here, and we subtract, okay, the brown square from it, this brown square, okay, in order to be left with just the orange area within the square. Let's find out how to write this down algebraically, getting the whole square and then subtracting the brown square from it. Well, we know that the area of the whole big square is in fact n squared over 4 multiplied by n plus 1 squared. So we're going to write that down. So the big square has an area, okay, that big orange square has an area of n squared over 4 multiplied by n plus 1 squared, okay? We already established this close to the start of the video. Now the idea is to subtract the brown square from it in order to get the area shaded in orange over here, okay? However, what is the value or the area of the brown square? Let's find out. Well, the brown square has a length and a height of 1 plus 2 plus 3 plus 4 plus ... plus n minus 2 plus n minus 1. If we look at the diagram carefully, we realize that. And because of summation rules, this means that the length and height, okay, is equal to n minus 1 divided by 2 multiplied by n minus 1 plus 1, okay? It's kind of similar to this formula over here, but you subtract 1 from n, okay, over here and over here, alright? So this is the length and the height of the brown square. Now, since the area of a square is its length times its height, okay, it means the area of the brown square is going to be equal to this over here squared. Alright, so it means that this orange area here is going to be n squared over 4 multiplied by n plus 1 squared minus n minus 1 over 2 multiplied by n minus 1 plus 1 squared. Okay, and since this over here is equivalent to this over here, let me just join them up. We have exactly the same formula as this, alright? Now what I'm going to do next is demonstrate why this formula is equal to n cubed, okay? And once I've done this, I will then be able to explain to you in simple terms what the area of these other boxes is, okay? Shaded in brown, purple, grey, blue, red, green and yellow. I'll be able to demonstrate what these areas individually are equal to, okay? But the first step is to understand this right here and to prove why it's the case so that it sinks in to your mind. So the area shaded in orange is equal to this. We are getting the big orange square and we are subtracting the brown square from it. Now let's prove that this is in fact equal to n cubed. Okay, so first of all, in here we've got n minus 1 plus 1. Alright, so we can get rid of the minus 1 over here and the plus 1 over here. So what we're left with is n squared over 4 multiplied by n plus 1 squared minus n minus 1 squared over 4 multiplied by n squared. Okay, now these fractions over here are similar, so we can isolate them in the equation. This means that we end up with n squared over 4 multiplied by, in brackets, n plus 1 squared minus n minus 1 squared. Okay, and we are going to simplify further from here. Now let me just write down this. N plus 1 squared is equal to n squared plus, let me just make this clearer, it's equal to n squared plus 2n plus 1. Okay, and we are subtracting this, and this is equal to n squared minus 2n plus 1. Okay, so this up here turns into this, and this is equal to n squared over 4 multiplied by, in brackets, well, we can subtract these, okay, 2n minus minus 2n is actually 4n, and 1 minus 1 is 0, okay? So we end up with this over here, n squared over 4 multiplied by 4n. The 4's cancel each other out, and what we get is n cubed, okay? That is n cubed. This means that the area over here, shaded in orange, is equal to n cubed. And this is essential because if we know that this is n cubed, we can discover these areas over here far more quickly, okay? Far more quickly. And I'm going to demonstrate why. Okay, so we found the area shaded in orange. It's n cubed. Now let's try to find the area shaded in brown. What's that going to be? Well, to find it out, all we need to do is get the area of the brown square, okay, and subtract the area of the purple square from it. We've already established that the area of the brown square is n-1 over 2 multiplied by n-1 plus 1 squared, okay? We've already established that because its length is equal to what is inside these brackets. We spoke about this earlier, okay? It's over here. So what we just need to do next is get the area of this brown square and subtract the area of the purple square from it. But what is the area of the purple square? Well, the purple square, alright, I'm just going to put this down over here. I'm going to code it. Has a length and a height of, let's see, 1 plus 2 plus 3 plus 4 plus ... plus n-2. Okay? That is 1 plus 2 plus 3 plus 4 plus ... Okay, plus, let me just check one more time, n-2. Okay, and according to summation rules, this is equal to n-2 over 2 multiplied by n-2 plus 1 in brackets, okay? So the area of that purple square is going to be this, alright, squared, alright, because we are multiplying the length by the height. This means that the area shaded in brown over here is going to be equal to this, what we've already written down, minus the area of the purple square, okay, which is, in brackets, n-2. Let me just make this clearer. n-2 over 2 multiplied by n-2 plus 1, okay, all in brackets, squared. This over here, this equation or expression over here, is going to be equal to the area shaded in brown. Now, because of this formula over here, alright, which is number 3, I wrote this down a long time ago, we can figure out what the value of this over here is going to be, okay? And that value is actually going to be equal to n-1 cubed, okay? Because all we do is go to this formula over here and we replace the n with n-1. And if that happens, we get n-1 cubed, okay? So the area shaded in brown over here is n-1 cubed. And a pattern is starting to emerge. We see the length over here as n, and we see that the area shaded in orange is n³. We see a length over here of n-1, and we see that the area shaded in brown is equal to n-1³. So we can kind of figure out what the area shaded in purple is. But so that I make absolutely clear how everything works, we are going to find out what the area shaded in purple is algebraically, and then from there we'll complete the proof. Now the area shaded in purple is going to be equal to the purple square and subtracting the grey square from it. Okay, if we do that, we're just going to be left with the area shaded in purple. We're getting the purple square and we're subtracting the grey square from it. Now, we already know what the length and height of the purple square is. Alright, I wrote this down over here. And this means that its area is this. It's length times height. So let's write down the area of the purple square, and then let's subtract the grey square from it algebraically. Well, the area of the purple square is n-2 over 2 multiplied by n-2 plus 1 squared. Okay, and we are going to be subtracting the grey square from it. Okay, to get the area of the grey square, we will need to know its length and also its height. So its length is going to be equal to 1 plus 2 plus 3 plus 4 plus, I'd say, n-3, okay? We can't see the n-3 there, but for the purpose of this video, I'm just going to say n-3, okay? So, the length of the grey square is 1 plus 2 plus 3 plus 4. Let me just make this clearer. Plus n-3, okay? And if the length is this, it means its height is also this. Alright? And 1 plus 2 plus 3 plus 4 plus n-3 is the same as n-3 divided by 2 multiplied by n-3 plus 1. Okay? And this means if we subtract the grey square from the purple square, we are going to get this over here minus n-3 over 2 multiplied by n-3 plus 1 squared. Okay? So this expression over here is going to give us let me see, the shaded area over here in purple. We are getting the purple square, okay, and we are subtracting the grey square from it, and we're going to be left with this purple shaded area. Now, what is this expression over here actually going to give us? To find out, we just go to number 3 here, the formula labelled in 3, and we replace the n's here with n-2, okay? If we do that, we are going to get n-2 cubed for this expression down here. That's going to be n-2 cubed, okay? And we know this because we've plugged n-2 into this formula over here, Okay, so this area shaded in purple is n-2 cubed. And of course, it has a length of n-2. Okay, this shaded area over here, right at the top, we can see the length n-2. And the whole area is n-2 cubed. As we can see, a pattern has emerged, or it had emerged previously, but now it's become even more apparent. Because here we have n cubed, here we have n-1 cubed, and here we have n-2 cubed. And we are getting closer to coming up with the proof. So we know that the area shaded in grey is going to be plus dot 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 plus. We know that the area shaded in purple is n-2 cubed. We know that the area shaded in brown is n-1 cubed. And we know that the area shaded in orange is n cubed. Okay? Now that the abstract parts of this proof are out of the way, we can deal with the concrete parts like 1 plus 2 plus 3 plus 4. Let's find the areas shaded in blue, red, green, and yellow, then complete our proof. The area shaded in blue is going to be the blue square minus the red square. Now the blue square, okay, has a length and a height of 1 plus 2 plus 3 plus 4, and the red square has a length and a height of 1 plus 2 plus 3. 1 plus 2 plus 3 plus 4 is in fact 10, and 1 plus 2 plus 3 is 6. Okay, so the area shaded in blue is going to be equal to 10 squared minus 6 squared. Okay? And what does 10 squared minus 6 squared actually give us? Well, this is the same as 100 minus 36, okay? And that gives us 64. And 64 is 4 cubed, okay? So we know that this area shaded in blue is 4 cubed. Alright, I've written that down over here. Now let's go about finding the area in red. And we get that by getting the red square and then by subtracting the green square from it. We know that the red square has a length and height of 6. Let me just put this down in black. And we know that the green square has a length and height of 1 plus 2, which is 3. This means that the area of the red square the area shaded in red over here is going to be the same as 6 squared minus 3 squared, okay? And that gives us 36 minus 9, which is the same as 27, which is the same as 3 cubed. Alright, so we know that this area shaded in red over here, just going to put an arrow towards it, is 3 cubed. Okay? Now all we must do to get our proof is find the area shaded in green and then the area shaded in yellow. So we're not too far away from completing it. Alright, the next step. Let's find the area shaded in green. Okay. to get that area, we'll need to get the green square and then subtract the yellow square from it. This is pretty simple. So we know that the length and height of the green square is equal to 3, and the length and height of the yellow square, okay, is in fact equal to 1. It's very small. We can see that it's equal to 1. Okay, so this means that the area shaded in green, if we subtract the the yellow square from the green square, we get 3 squared minus 1 squared, okay, and that gives us 9 minus 1, which is 8, and this is 2 to the power of 3, okay. So the area shaded in green over here is 2 to the power of 3. Now the area of this yellow square is simply 1, okay, and 1 is the same as 1 cubed. So we're just going to call this shaded area in yellow 1 cubed, okay? And because we have all of this information now, we know what these shaded areas are, we can go about completing the proof. Now make sure you're ready for this. Get a pen and paper, because we are going to complete this proof, okay? So inside this massive square, what we have is 1 cubed, okay, plus 3 squared minus 1 squared, plus, let me just go up here, 6 squared minus 3 squared, plus 10 squared minus 6 squared, okay, plus dot 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 plus n minus 2 over 2 multiplied by n minus 2 plus 1 squared minus n minus 3 divided by 2 multiplied by n minus 3 plus 1 squared, okay, plus, let me see, n minus 1 divided by 2 multiplied by n minus 1 plus 1 squared minus n minus 2 divided by 2 multiplied by n minus 2 plus 1 squared, okay, and then plus n over 2 multiplied by n plus 1 squared minus n minus 1 divided by 2 multiplied by n minus 1 plus 1 squared. And this gives us, according to our calculations, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus dot 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 plus n minus 2 cubed plus n minus 1 cubed plus n cubed. And this is equal to the sum of the cubes of all natural numbers up to n terms. Now here's the special part. Because all the shaded areas okay, make up the entire big square, we end up with this being equal to n squared over 4 multiplied by n plus 1 squared. Okay, this over here is the area of the entire big square, and these shaded parts make up that entire big square. Therefore, we have our proof. We've proven that this is equal to this right over here. Now you can replay this video again to check all the results. You can watch it as many times as you want. I know it hasn't been the perfect video, but I believe there isn't anything like it online at the moment. If you liked this video and you like my work, follow me on Instagram. Here's my Instagram page. You can see it on the screen. Follow my mathematics proofs page on Instagram as well. You can see it on the screen. And stay subscribed to me on YouTube. I'll see you around, and thanks for watching.